Good afternoon, everyone. Thank you very much for having me here. Thank you to the Faculty of Sciences for inviting me. And I'm going to tell you about the real star today, which is that telescope that's sitting up there, the James Webb Space Telescope. It's the world's newest engine for discovery of the cosmos. To start out, though, I want to talk about telescopes in general. You see four pictures up here. The one on the top left is actually an X-ray picture of the Crab Nebula. The one on the upper right and the lower left are Hubble Space Telescope images of objects within our own galaxy. And then the bottom picture is a collaboration of three telescopes in orbit. An X-ray telescope, this is known as the Chandra X-ray Observatory, the Spitzer Space Telescope that now no longer is operating, and the Hubble Space Telescope. What these are different eyes on the universe. Every time we look at the universe with new eyes, we see things differently. It's a diversity of viewpoint that I'm going to come back to later, but it's this very beauty that enriches. One of the things that the Hubble Space Telescope did many years ago was stare deeply into space and take this picture you see here. This was known as the Hubble Ultra Deep Field. It's now almost 10 years old, and until recently was the deepest picture humanity ever had of the cosmos. With the exception of two objects on that picture, everything is a galaxy, trillions, tens of billions of stars in each one. Importantly, there's something missing from this picture, and that is the very first galaxies that formed after the Big Bang. Hubble was the culmination of a century-long effort to find the first stars and galaxies, and it could not do them. Not because it's not an amazing facility, but because those objects were farther and fainter than what Hubble could see. So, since we're all here talking about science, we're going to have a little brief physics lesson because that's what we all like to think about. And what I'm showing you here is a picture of what's known as the black body spectrum. So how much energy comes out at a given wavelength for an object that is a specific temperature. In this case, this is an object that's about 3,000 degrees Kelvin, or like that of a cool star. And you can see that most of that emission comes out somewhere just shortward of 1 micron, so in the part that we can see our eye. And that, you'll also see the notation Z equals 0. So astronomers measure distances to very far things as redshift. We'll come back to that. But we illogically use the variable Z to stand for redshift. So Z of 0 means something that is nearby. It has 0 redshift. Now, if we're looking out in space, we are also looking back in time because the speed of light is finite. And so if we go back to a shift of 3, that means the wavelength has been shifted to the red. The very expansion of space has stretched the wavelengths of light so that what was before a cool star emitting most of its light in the visible, by the time it gets to us, now it comes out in infrared. And if we redshift an object even farther, about to the redshift of the farthest objects that Hubble would have seen in that picture I showed you earlier, well, now you're at a redshift of about 10, and you can see that the peak of that emission is coming out at about 10 microns. So this tells us one reason why we needed to have a different telescope. That is the light that we were chasing, the chase of galaxies. We need to look in the infrared if we want to see it. That's where most of that energy is going to come out. So Hubble's visible optimized, we need to build an infrared optimized telescope. So that's fact one about Webb. Another consequence of this expansion of space is not only is the light wavelengths are they stretched, but things get fainter. In fact, that same object at a redshift of 10 that was there at Z of 0, it's about 10,000 times fainter. So we needed something that was infrared optimized and bigger than Hubble to collect the light. So those are pretty much the two simple physics facts that tell you what you needed to build to complete one of the missions that Hubble was designed for. Now, I'll also just mention this as a side benefit. If you're optimized for the infrared, you're a local object and a temperature of 3,000, best seen in the visible. But if you start looking to the red, you become sensitive to cooler objects. So this is another view that you get of our own nearby universe. You see different things. You see cooler things, and you can also see through dust. Radiation penetrates dust in a way that visible light. So this is the simple graph of what we wanted Webb to do, just to look for these first galaxies. Hubble can see when modern galaxies, that is, galaxies filled with heavy elements like you and I are made up of, carbon, nitrogen, and oxygen, can see those, but we needed to see back to when the first galaxies formed. And in terms of time, Hubble can see back to maybe 450 million years after the Big Bang. Already with Webb, we're talking about seeing 3 billion years. So even though we haven't even completed 1 year of observations with Webb, we're already exceeding what Hubble has done, and we think we'll be able to fulfill that promise of seeing those first galaxies. Since I work at headquarters, I have to deal with a lot of non-fun physics and engineering things, that have a policy and money things. And so I have a chart. I don't expect you to read the fine details of it, but these are just important events that have happened over the nearly 30 years it took to develop Webb. And in fact, if you look at that in terms of US presidencies, we've had to do this through all these different administrations, which means we have to ask for this money. The way the government works in the US, you have to ask for your money every year. So it's important to have these compelling science goals because they need to be sustainable over a long time, and you have to convince many different people of the importance of it. So as you all are thinking in your careers about science, not only is it important to do the science, you need to be able to tell smart scientists about the importance of your work because you're going to have to convince those people over many years to keep providing you funding. So that's just a side advertisement for the boring part of my job. Hubble and Webb, you can see all the different sizes. Webb is much larger physically, it's much lighter. It's comprised of materials that are much more advanced and designed to be lightweight because we want to throw off any extra mass that we didn't need. The other thing I'd like to draw people's attention to is just how different it looks from what most people think a telescope looks. People are pretty familiar with telescopes looking like Hubble. It's a tube with some glass at one end of it. Webb looks like a space in the future. It's got this big naked gold mirror sitting out there. In fact, it's about the same amount of all the gold. If you took all the gold in Webb and swept it up into a small mass, it's about the same mass as a golf ball. It's just spread over that giant mirror to be about 1,000 atoms thick on the surface coating. So I think it's this actually beautiful design for Webb that also is important thing in its use because it looked interesting to people. But that interesting look comes with engineering implications. To put together Webb meant that you had to take something that was bigger than the rocket fairing you were going to launch on and stuff it into the rocket and launch it. And so over most of that time, this is really a tribute to the engineers whose creativity and hard work enabled this amazing scientific mission. Now I have just a few little charts, mainly to remind me to talk to you about what these challenges are. The one in the upper left is that very challenging effort of fitting something that's bigger than into it. So that meant we had to fold everything up to fit inside of it. The chart in the middle that has the blue back and the little red devices on it, that's meant to show you that the materials we had to build Webb out of needed to be very stable because when you manufacture something, you're manufacturing at room temperature. That's how we make things. But Webb has to work, as you may remember for that last chart, at nearly absolute zero. So you have to test it at absolute zero. You have to know how your material is going to change when you manufacture it at room temperature, take it and test it at cryogenic temperatures, and then bring it back up to room temperature, because eventually you launch it at room temperature. So you had to do a lot of material science to make sure you understood how these materials behaved with temperature. The very confusing graphic at the bottom middle there is a little chart showing the heat flow from the bottom. The heat source for Webb is, of course, solar radiation, the input from the sun. And at the top is the cold telescope that shouldn't be giving off much energy, because being infrared optimized means we're looking for heat signals, so we don't want the telescope to be warm itself, otherwise you're just swamped by the signal. We had to trace how heat flows through that system to watt level. We had to know where milliwatts of energy were going at any given time. And a milliwatt, just for rest, about the resting energy of a flea. So that amount of energy we had to know where it was being traced. And then the chart on the right is my reminder. It shows the telescope in a test chamber at the Johnson Space Center, a giant chamber where we took it down to these cryogenic temperatures, because that's the part of the telescope that was cold. The spacecraft part with the sun shield always stays warm, so we were never able to test the whole system as one. In the space industry, we have a saying called test as you fly, which means you're supposed to do all your testing in the configuration that you will eventually fly. Couldn't do that for Webb. No testing chamber in the world was big enough, and it's not even clear that we could have made a chamber to simulate the environment the way we needed. It would have cost probably more than the telescope itself. So we test and build and test the two halves separately, and then through very accurate computer modeling, say that those two pieces would work and behave the same. I sometimes refer to this as our 11th technology, that we had to invent simulations so good that we could not only trace those milliwatts and how the structures move by nanometers, and then have faith that those models would give us an accurate representation of what eventually flew. In addition to that systems level computer modeling, we had to invent physical things for Webb. There were about 10 in all. Here are just a few we can put down there. We invented little micro shutters those little shutters are about the diameter of a human hair, or smaller than a human hair, and we can open and close those electronically to view different parts of the sky. We had to invent a refrigerator system, a cryocooler, to cool one of the detectors on our telescope to 6 degrees Kelvin, 6 degrees above absolute zero. The back plane was that super stable structure. The lightweight mirrors, they're actually comprised of beryllium. Each of those 1.3 meter hexagonal segments is a big chunk of beryllium that we made. It's about yay thick. And then after making that billet, we hog out the back of it, clean out the back, so 95% of the mass we want to be recycled. And then we coat it with those 1,000 atoms of gold. So in some sense, you use the whole thing just to take 1,000 atoms of gold up there to collect your light. Why gold? It turns out gold is actually very reflective in the infrared. It's about the best substance you can use, so that's why we use gold. Then there was some electronics that we needed to invent too, because all those wires that you think of going between components of a spacecraft, well, they carry energy, which means they carry heat, and we don't want to carry heat around, so we had to invent some cryogenic application-specific integrated circuits. And then lastly, we had to invent a new material for that sun shield. We'll talk a little bit more about that. This is just a little quick diagram showing you, how light hits that big gold primary mirror, bounces off a gold-coated secondary, and then it goes into that conical structure, and there's another couple of mirrors in there before being dispersed out to the instruments. You see the different types of optical prescriptions, and then the chart on the bottom right is to show that in that picture, if it's all one color, that means it's good, it's very smooth. And so the left picture you see is different colors. That is when we have this mirror at room temperature, it is imperfect. We know it's imperfect, but we polished it so that when it gets cold and it changes shape, it's perfect when it's cold. We can also adjust it on orbit. There are actuators to move it, so we have that flexibility. This is a bit of an eye chart. It just has details about the science instruments. The important thing to remember here is that we have 4 science instruments on Webb. They came from the University of Arizona, working with the company Lockheed Martin. Dr. Marsha Ricci at the University of Arizona was the principal investigator. The NIRSPEC instrument was provided by the European Space Agency. The MIRI instrument is a collaboration between the European Consortium and our own Jet Propulsion Laboratory, and the European lead for that instrument is Dr. Julian Wright. The fine guidance sensor and NIRIS, the near-infrared imagers of the spectrograph, came from the Canadian Space Agency. This is one place where we see diversity really helping out Webb. We have instruments from all over, harvesting the best knowledge of all over the world. And I will point out that 50% of our science instruments were led by women. I mentioned these stable cryostructures, that backplane that holds the telescope mirrors. We need to know how they change their behavior. There you can see to 38 nanometers, 1/10,000th of human hair. We have to control that structure to that level. And it's doing even better than that. So this was an amazing feat by engineering. Just as a little foreshadowing, the telescope that will eventually come after Webb in maybe 20 or so years, there we have to control its structure to picometers, smaller than the diameter of an atom. So, some fun coming up. That sun shield is about the size of a tennis court. There are 5 layers in it, and we use those 5 layers to reject heat from the sun and also to protect us from micrometeoroids, because we know they're all around in space, they're going to be hitting us, but having multiple layers gives some protection so you don't get a hole that would let sunlight through. And if you do the calculation about how much energy is rejected coming from the sun and going out the top, those of you who know the sunscreen number, it is an SPF of about 10 million. And as someone with nerve, I really appreciate that. This is the final construction. This is the most deployed Webb ever was on Earth. And this is a picture from the clean room at the Northrop Grumman facility in Los Angeles. There you can see all 5 layers of the sun shield deployed. The primary mirror doesn't have its wings deployed, and the secondary tower isn't down. And that's just a limitation of how the crane operated in that room. So this was the most we could do at any one time. But it gives you a good sense of scale because you can see the 3 technicians working around it. So if we can get this to run, this is a little movie that's going to show you where Webb is operating now and how it operates once it's there. So let's see if we can get that to play. Oops, I've got myself stuck here, I think. Oh, I see the... Get some assistance on that to describe what would have happened in this movie. So this showed that Webb actually operates at the second Lagrange point. Remember, it's an infrared telescope, so we want it to be far away from sources of heat. The Earth is a tremendous source of heat, and most telescopes operate in low Earth orbit. We need it to be farther away from Earth, so we wanted to have this at about 1.5 million kilometers. It should be a movie there. Okay, I'll just do it. So at the second Lagrange point, which is a semi-stable point in any two-body system, there we orbit about the L2 point. We're not actually stationary. And L2 follows the Earth around the sun. So think of us being just going with the Earth as we go around the sun. We're just 1.5 million kilometers farther. There we can also communicate back to Earth very easily. It's 4 light seconds, so we have a pretty instantaneous communication. And we scan the sky in an annulus. So because that telescope is open, we can't ever look back towards the sun, and we can't look too far away because sunlight would hit either the front of the mirror or the back. So we're always looking more or less perpendicular to a line from the telescope to the sun. And then we can rotate around that axis. So you scan this annulus, and over the course of a year, it means you can see the whole sky. There are some pieces of the sky that are visible all the time. We call those continuous viewing zones, and it's there where we'll take our deepest pictures because we can look at those all the time during the year. The next little video is just a video of the launch that happened on Christmas Day last year, and it was out of French Guiana because one of the other contributions that the European Space Agency gave to the mission, in addition to those science instruments, was a ride on the Ariane 5 launcher. And it was a perfect ride, and I can't really thank ESA enough for the job they did there because they basically did such a perfect injection into orbit. They saved us enough fuel that we will last for more than twice our lifetime. We knew this almost immediately after the launch because we saw our solar array deploy. That wasn't supposed to happen until the spacecraft had time to correct its injection velocities. It didn't even need to. The computer loop that was supposed to do that check never ran once because the injection was so perfect. So even though the launch was only about less than 2 minutes old, we knew, uh-oh, this is going to be really good. And it turned out to be essentially perfect from a launch perspective. I mentioned the diversity points from a telescope perspective early in the talk. This slide was places in the world that have pieces of hardware or substantial software efforts that contribute to web. I believe one of its successes was this very fact that so many people from so many different places collaborated on web. This is the future of astronomy. Astronomy is a worldwide endeavor, and I expect at future telescopes this map is going to be filled in everywhere. So I can't wait for the day when the Moroccan dot is on the map, or perhaps several dots there. The next time we knew things were going really good on web was when we had the first focused image that came from the telescope. So those of you who are old enough, and I don't think it's almost anybody in the audience, are all very young, so that's great. When Hubble first launched, it didn't have such a good first picture. Now eventually it was fixed, but Webb's first picture, we had all those 18 segments working together, was absolutely breathtaking. And this is almost a picture if you could somehow, put your eye up to an eyepiece on Webb through all the instruments that are back there. This is what you would have seen if you looked, of course, if your eyes were sensitive in the infrared, if you would have looked at the Large Magellanic Cloud. So the fit is sharp. It's twice as good as we asked for. Each of the instruments is behaving more sensitively than we thought it would. I think I have a chart on this later on too. So this image that came down, I think in April, was the first scientific verification of just how good things were going to be on Webb. And I know somewhere there's footage of the day at the Space Telescope Science Institute when it revealed how well this was focused. And you can see everybody in that room, they're having a good day when those images come up. These are just a few of the images that got released on July the 12th of 2020. This is the Southern Ring Nebula. The picture on the left is a near-infrared image, so that's the shortest wavelengths that the Webb works at. This is a picture of a dying star. The star has ejected its outer atmosphere. As stars age, some stars of certain masses, they begin to pulsate and throw off layers of their outer atmosphere. This is actually a double star system, and the picture on the right is the mid-infrared picture. That's that mirrored instrument with the super cold 6 Kelvin detector. I want you to notice in the center of the picture on the right, there are 2 stars. On the left, there's only 1 star. Turns out the star that's giving off all those layers is the star on the left that you couldn't see in the near-infrared picture, but you can see in the mid-infrared picture. It's cooler. Think back to that chart where we showed how seeing at different temperatures shows you different things. Here we see the star that's actually giving off the atmosphere with just the longest wavelengths on Webb. And also being a person who, when I was doing active research, I studied galaxies, I always like to point out that really thin galaxy at about 9:30, 10 o'clock there. You see it both in the near-infrared and the mid-infrared. The mid-infrared, you're seeing just a big lane of heated dust in that galaxy. This is a group of galaxies known as Stephan's Quintet. It's 5 galaxies that appear to be all in the same place. The leftmost object is actually much closer to us. It's about 50 million light years away, and the others are more than 200 million light years away. So it's just a chance superposition, but there are 5 of them there. The one on the left, you can actually even see individual stars in that galaxy. The other 4 are in an interacting system. And if we look, if I just flip back and forth, this is the near-infrared view is dominating. This is just the mid-infrared view. And I want you to notice the topmost galaxy. You can see it's got a bright center, more or less in this one, but here you really see it booming through. There's an active galaxy in there. So it's a giant black hole that's swallowing up material around it and creating a super bright energy source. And we see it in the mid-infrared because there's a lot of dust around it. That dust is even blocked by the near-infrared that comes to us in the mid-infrared. We can use those spectrographs to look at what that environment is near that black hole. And the chart on the right shows all the elements we're seeing there, from the argon, neon, and the noble gases. Silicates are the dust that's surrounding it. And for those of you who may have looked at spectra before in the lab, the fact that those spectra are so sharp, again, tells us how good the system is performing. It's very precise, very high signal-to-noise spectra. Well, speaking of spectra, and moving a little bit closer, we looked at an exoplanet for those early release observations. This is one called WASP 96b. It was thought to have water based on previous observations with the Webb data, which are the white dots. You can see that it was confirmed without a doubt. The blue is the model of the water spectra. This may be one of the most famous pictures to come from that early release. I guess it was deemed the Cosmic Cliffs. It is a region where stars are being born. Along the top of the crest of that cliff is where gas and dust are being compressed by ultraviolet radiation that's coming from stars that are off the top of this picture. And in that compression, they are beginning to form new stars. And that very sharp edge, which is a feature of Webb data, comes from what are known as polycyclic aromatic hydrocarbons, and those are molecules that are found throughout space, but they can become building blocks of light, the PAHs. And this was the other one that was very famous from that day. This was, again, Webb hardly trying with this just a few hour picture. We took the deepest picture humanity ever took that day. And this is a picture of a cluster of galaxies, the white sort of elliptical nebulous objects in the front. But the mass associated with those and all of the galaxies there are bending the light from distant galaxies behind them and stretching their images, just how a lens can distort an image. Well, these are distorting galaxies behind them. And in fact, it's a way we'll use Webb. It distorts and magnifies. So we'll use nature's own telescopes, gravitational lensing, to study distant galaxies. And this was just our first attempt at it. So from the very far to the very near, we looked at objects in our own solar system. Here you can see Webb's view of Jupiter. You can see the ring of Jupiter very clearly in this one. Jupiter is very bright for Webb to look at, so you see some diffraction from the aurora just because they're so bright. But I'd like to show this picture, and this is a beautifully processed image. This was not done by folks at NASA. This was done by those, by Ricardo and Judy, whose names we all know. They are amateur citizen scientists. This is another reason why we believe it's important that the data are available, because you never really know who can do amazing things with it. This is now a picture of Neptune. You can see Neptune's two rings, and the bright, the six-pointed object you see is actually Triton, Jupiter's moon. Triton is the second most reflective object in the solar system, and so it's almost blinding for Webb. And just one tidbit, if you ever see a picture and you count the number of spikes the stars, if it's got 4 spikes, it's a Hubble picture. If it's got 6, it's a Webb picture. That's how you can tell them apart. And then we had also this earlier data on WASP 39b, but I think I've got a better spectrum of this later on. This was some confirmation of carbon dioxide in another exoplanet system. One of Hubble's most famous pictures was in the Eagle Nebula, the so-called Pillars of Creation. That's on the left, a visible image, and on the right is the near-infrared image. And you can see it looks like it's peppered with more stars. That's because we're seeing stars that were previously blocked by dust in that nebula. And then you can see clearly the difference between the 4-point star and the 6-point star here. The other feature that almost every Webb image has, because it goes so deep, so fast, is that there's a lot more galaxies in this picture. In fact, it used to be when I studied galaxies, I always thought of stars as I got in the way of the galaxies I was looking for past them. Now people who study stars are finding, oh, there's just too many galaxies in the picture. Now the galaxies are getting in the way. I say turnabout is fair play there. This was a recent image. I think it came out maybe a week or so ago of a protostar. So this is this is a star that's being formed. And if you look very closely at the center of this picture, you can see a black line going through it. That is the nebular ring of dust out of which a solar system is being born. And all that material above and below it is being illuminated by that young stellar system as it is being born. And you don't see the light out the sides because it's getting blocked by that thicker material that's accreting around it. This is now, I think this now ranks as about the deepest picture we have of the universe. And again, it's another cluster of galaxies. And the two things I want to call your attention to here are the two boxes in the center, where again we have that Z variable that measures redshift for astronomers, and that one on the bottom, a little red smudge in the middle, has a Z of 12.5, and that's the one, again, not even 1 year into Webb, and we have seen farther than we have ever seen before. And it's only going to get better the longer Next, I want to talk about how you can look at these data. All these data from Hubble, Webb, TASS, a mission known as the Transiting Exoplanet Survey Satellite. All these data sit in what's known as the Mikulski Archive for Space Telescopes. And anyone can go there and download the data. I think you just have to sign up, give them an email address or something like that. Now, the archive is constructed primarily for scientific use, but anyone can go there and query the archive if they know what they might be interested in, or they heard about that Pandora's call. They wanted to go pull those pictures. They could do that at this archive. This is, again, the open science. We're finding returns, benefits much quicker than keeping it closed. We would have gotten probably the same scientific results. We wouldn't get them as quickly, and we don't get as many different interpretations of things. So I encourage anyone who's interested to Google Mikulski Archive, also known as MASS, and you can get the data from all those missions there. I mentioned that citizen science picture. The other link that I think is really important on this page is that one at the bottom. Anyone with an observatory, or if you had a large telescope yourself, you could participate in monitoring potential targets for Webb. You can go to that URL and they tell you how you can participate in that program. And I think the whole field of exoplanets is really going to be this century's grand undertaking for astronomy. And all of you who reach now, you can get in the ground floor. So get in before the elevator takes off there. Webb, we're already seeing it has impacts beyond astronomy. I know that Hubble pictures were used for albums and CD covers, and we're beginning to see recognition for Webb outside of the scientific field. So that's very gratifying to see. Not totally surprising, because I think people really enjoy astronomy. It's a little part of our souls, but it is nonetheless, it's wonderful to see it getting acknowledged. Times when people, somebody from NASA comes to talk, they want to know, is there anything practical that has come out of this? There are some things already that has come out of Webb. I think the one that has enjoyed the biggest commercial success is the technology that we use to measure those mirrors when we were manufacturing warm and taking cold and then bringing back the warm. The people who invented the optical measuring device for that have now commercialized that. People who are going to have surgery, they use those devices. So the same technology that made our mirrors can map your eye very accurately. Got a couple of links I want everyone to share. Of course, like almost every person or inanimate object, there's a Twitter account and an Instagram account and a Facebook account for Webb, and it uses that name. If you want to see latest press releases or latest news about Webb, you can go to nasa.gov/Webb. And then at the Space Telescope Science Institute, which operates Webb for NASA, they have a wonderful site, webtelescope.org, that not only has these latest releases coming out, but good science background stories on them. And then for those of you who want to get into the more scientific end of Webb, there is a Facebook, Twitter, and YouTube account for JWST Observer. There are videos you can watch about how you can actually propose to Webb, how you can analyze Webb data, and the 3 links you see below, the one at spsci.edu/JWST, that's the primary science door to Webb. If you're a scientist and you want to do things with Webb, that's a link you would use. The archive is that Mikulski Space Telescope archive. And then if you just want to see cool pictures of Webb being built, or little movies about it, that bottom link, SBS stands for Science Visualization Studio. It's a big website that has all kinds of photographs for things that the Space Flight Center, which was the lead management center for Webb. They're there, so you can go there and just use a search engine for Webb, and you can see pictures from when it was just a few pieces of hardware to when it was finally built. So, I think I'll just actually leave that there. Take any questions you want, but we really want you to come on the journey because it's going to be a fabulous one.